Before watching this video, you should have a good understanding of how to draw Lewis structures that contain only single bonds. So up to this point, everything has been working out perfectly when you've been drawing Lewis structures. The number of valence electrons that you start with is the same number of valence electrons that you end with, and everything just works out. In this video, I'm going to show you what happens when things don't work out, when we have more valence electrons represented than what we have in our structures, how to compensate for that, how to deal with that. So let's start by drawing the Lewis structure of carbon dioxide. So we have one carbon and two oxygens. And I'm going to follow all the same rules that I followed when I was drawing Lewis structures that contained only single bonds. So I have one carbon in this structure, and each carbon brings 4 valence electrons to the table for sharing. Remember, in covalent bonding, we are sharing electrons. The two oxygens each bring 6 valence electrons to this compound, to this molecule, and we have a total of 12 valence electrons from the oxygens. Now, if we add these up, we get a total of 16 valence electrons. That means that we have to represent 16 valence electrons in this Lewis structure. So the next step is to draw out my skeleton structure. Now remember, carbon always goes in the center. So when you don't know how to draw, when you don't know where to start with this, always put carbon in the center, and remember, hydrogens always go on the outside. So the next step is to form my bonds, and I'm also going to complete the octets. So I have oxygen here is surrounded by 8 electrons. I've added dots so that carbon is surrounded by 8 electrons and oxygen is surrounded by 8 electrons. Now remember, this is the reason why atoms bond, so they can complete their outer shell. Now, if I go back and add up how many valence electrons are represented in this structure, I get 20 valence electrons. Now, something isn't right with that. You're probably used to this working out perfectly, where the number that you started with, that 16, equals the number that you end up with, the 20. Well, as you can easily see, they don't equal each other. 16 does not equal 20. So what do? Well, take a look at these two pairs of electrons. What we're going to do is we are going to get rid of those lone pairs, and in the place of that, add a bond, add another bond. We're not really adding another bond, we're just adding 2 shared electrons to the bond that was already there. So if we are going to now add up the number of valence electrons, we get 18. Now you can go ahead and pause the video and count the number of electrons represented on each atom. You will get an octet, but we have 18 valence electrons represented, and we should only have 16. So what we're going to do is we're going to do this again so that we get to 16 valence electrons. So the 2 lone pairs that I've represented there, I'm going to get rid of those and in the place add 2 more shared electrons. So now look at each atom. Oxygen is surrounded by an octet, carbon is surrounded by an octet, and the next oxygen, the second oxygen, is surrounded by an octet. And if we count up the number of electrons represented, the red, we get 16 electrons. So 16 equals 16. Now, why did I add that second extra bond between the other carbon and the oxygen and not draw it like this, where I have the carbon in the center and 3 bonds between one of the carbons and the oxygens, and only 1 bond between the other carbon and the oxygen? So looking at this secondary way of drawing this, we have all of our octets completed. We have 16 valence electrons represented. So why did I not draw this structure? Well, the answer lies in bonding preferences. Ideally, oxygen would want to have 2 bonds or a double bond, and ideally, carbon wants 4 bonds. So what we have here is we have in the top option, we have carbon having its 4 bonds and each of the oxygen having 2. The bottom option, we have carbon having 4, which is great, but one of the oxygens has 3 and the other one has 1. So if we look at bonding preferences, it will tell us that the top option is the one that is the likely drawing for the Lewis structure for carbon dioxide. Now I want you to pause the video and try to draw this nitrogen molecule on your own. So the first thing we have to do when we draw this molecule is determine how many valence electrons we want represented. So we have 2 nitrogens, and each nitrogen has 5 valence electrons. So we have 10 total valence electrons that we need to have represented in our structure. The second thing that I want to do now is draw our skeleton structure. So this is super easy. We have 2 nitrogens in it. Then I connect the 2 nitrogens by a bond. Remember, one bond represents 2 shared electrons. The last thing I want to do is complete the octets. So nitrogen needs to be surrounded by enough dots so that the octets are completed. And when I add up the total number of electrons represented, I get 14 valence electrons. That's too many. I only want 10. So I need to get rid of 2 lone pairs and add another bond. So I'm going to get rid of 2 lone pairs here and add another bond. Go back and look. I have all my octets represented. So I still have octets represented, but now I have less electrons shown in my molecule. I only have 12 valence electrons, but it's still more than 10. So what do I need to do? I need to do this operation again. I need to get rid of 2 lone pairs and then add another bond between the 2 atoms that I have removed lone pairs from. So now if I look at both nitrogen atoms, they are surrounded by 8 electrons. Remember, each bond represents 2 shared electrons. So I have 2, 4, 6, 8 on nitrogen 1 and 2, 4, 6, 8 on nitrogen number 2. When I add up the total number of electrons represented, I get 10 valence electrons in this structure. Now, in carbon dioxide, we have what is called a double bond. Sometimes I use the terminology as 2 bonds, but really it's just 1 bond that's stronger. And in nitrogen, I have a triple bond. This is a total of 6 shared electrons. Sometimes I call it 3 bonds when I'm counting up my total number of bonds, but it's really just 1 bond that's much, much stronger because now 6 electrons are being shared. So this is a triple bond.